Um, okay, anything else you want to say about the warm-up before we begin? Actually, wait, hold up. I'd like you to do like a part D on the warm-up, if you will. Could you do the last one, part C, and just do like, make that upper limit be 50 instead? Could you do that, please? From 0 to 50 instead. It won't be. We're going to add like 30 more terms, Maddie.
I'll do it, but
Just do it. Oh, and when you're done with that, part E, I'd like you to do the same one again, but then 0 to 100, if you will. Could you do that? And then I'd like you to add a part F to the warm-up too. Could you do 0 to 1,000 as well? Okay. And then a part G, if you could make that 0 to a million, that would be good. Just keep doing the same problem, just change the upper limit. And then part B, C, D, E, F, G, H. Part H, can you go from 0 to a billion, please? And then part I, if you could add a part I as well. Do you have a conjecture to make around what I've just asked you to do? Can you make a conjecture about this particular series as we increase the limit of the top limit of the sum? It's closer to 8. Okay. Is that what people are finding? Okay. Interesting. We're gonna have to plumb the depths of that one. All right. We'd like to talk about that. In fact, that notion today. This idea of an infinite series, an infinite sum. How can that even be meaningful? I hear you cry. Now, I should give you a warning. This is a tricky area. And as we begin, I just want to give you a warning to, take hold of your hat, young fellows and young ladies.
We should bring hats back.
Yeah, we should bring hats back. So the question, to be more clear, the question is, can we make any sense of this symbol? Does it even make sense at all to put an infinity at the top of one of these crazy sums? The answer maybe is yes, because otherwise I wouldn't be here today talking about it. But we'd like to make sense of what that could possibly mean. Here's the way that mathematicians make sense of it. I think you'll like it. It's the same sense that we just used a second ago as I added parts to the warm-up, right? I said, what if you were to increase that limit, the upper limit of the sum, to a higher number, and then a higher number, and then a higher number? Each one of those sums is perfectly well understandable and well defined in ways that we've already talked about, right? Like, it makes complete sense. You're just adding up a finite number of terms. And the question is, each one of those sums that I asked you to compute is not the infinite sum. It's only a partial sum. So we call those each a partial sum. And if that number, each time you get an answer to part D, and then part E, and then part F of the warm-up, if those partial sums seem to be approaching 8 or whatever, then we say that that's what the sum equals, the infinite sum. So, for example, in the warm-up today, if we had replaced that 20 with an infinity, we would have said that that sum equals 8. Does that make sense? All right, let me see if I can remember the problem. I'll write it over here on the board. It was the sum from n equals 0 to 21 of 2 times 3/4 to the n, right? 20, yeah. But what I'm saying is if we replace that upper limit, who cares, 20, 21, 50, 100, whatever. If we replace it with with infinity, then this equals 8, is what we're going to say, right? And I guess the key thing to see here is this, right? Oops, there. That piece right there. Notice that this symbol, when we started with the infinity at the top, made no sense to us, maybe. But this makes really good sense to me. For any particular n value, this sum in here, the sum from k equals 1 to k equals 50 or something, makes complete sense and is perfectly well defined. And all I'm doing is asking, what's the limit of that expression? as n approaches infinity. To be clear, I want to make sure you understand that this is a different limit than we've talked about already. We talked about the limit of a sequence already, didn't we? The limit of this sequence, the actual terms of this geometric sequence is what? The actual limit of the terms themselves. If you actually write out the terms, the first term is 2, and then the next term is 6/4, and then 6/4 times 3/4 again. And, okay, what is the limit of those terms themselves? Think about the behavior of this as if it's a function. It's 0, right? The terms themselves go to 0. Do you agree? Yes. The limit of the sequence is 0, but the limit of the series is 8. You see that there are two limiting processes that I'm asking you about? I want to make sure you have those straight in your head. Okay? Make sure that's really clear. This is the second thing I'm thinking about, is adding them all up. That's clearly not 0. That clearly approaches something that's already positive because it starts with 2. And then we just go up from there. Apparently it approaches 8. All right. Are you good now? Whoever asked me to pause. Okay, thanks, Dave. All right. So when do infinite series converge? This is an interesting new notion to us, so we want to think about this now. What infinite series could I hand you that would actually have an answer here? Because it's a limit. Sometimes limits diverge. Well, I think we can say, and we can maybe come back through and give some more formal justification for this later, but that arithmetic series do not converge. That's for sure. There's never a time when you add up an infinite arithmetic series and get a number. That's not arithmetic, though. Nor does it converge, but that's a different issue. Okay. Let me give you our sum formula for yesterday for a geometric series. Am I right? It was this. Am I right? Okay. That was our sum formula for a geometric series.
Yes.
Yes. Now, I want to ask you the question, what happens when r is a number that's less than 1 in absolute value, and n gets large? What happens to this piece right here? What happens to r to the n when r is a number like a half?
It gets closer to
Or 3/4. And n is like a million. Yeah, this piece, this r to the n piece, goes to 0 as n gets large. If r in absolute value is less than 1. Giving us the following infinite sum formula for a geometric series, provided r is less than 1 in absolute value. Oops. Wait, yeah. Do you see how that formula comes about? I don't want you to think about this in a different place in your head than you do the geometric sum formula. I hope they're connected for you. Do you see how one gives rise to the other?
Sure.
I'm just saying, if you make this piece go to 0, if the r to the n piece is 0, then you just get a 1 over 1 minus r. You said it, not me. Can we just verify quickly that that works for this problem in the warm-up? What was the first term? 2, and the common ratio was 3/4. So is it true that 2 over 1 minus 3/4 is 8?
Yes.
Work it out and see that we're right, because I hope we're right. It'll be good. I've just given you a thing of beauty and power here, this formula, for an infinite geometric series. We're just adding an infinite number of things up. You should stop to appreciate that. I mean, it's my opinion that you will look back on this day as a life-changing moment. Like someday, years from now, you'll be like, I can remember it was April 14th, 2016 that my life changed forever. And we're just beginning, ladies and gentlemen.
If I get famous, I will remember you the second.
All right, let's take a look at a couple series. And I actually want to not just think about the sum, I also want to think about the partial sums along the way like we suggested. So this first one, for example, 0.3 plus 0.03 plus 0.003. By partial sums, let me just make sure you understand what that means. I want to add up not the infinite series, but just a part of it. So what's S1? The sum of the first term. It's a dumb question, but it's just 0.3, right? What's S2? The sum of the first two terms. Very good addition skills, class. And then, oh wow, you guys are really sharp. Okay. No, I can't even write as fast as you can think. That's amazing. Good job. Okay, etc. These are, let's make sure you understand, the partial sums, each of these sums is a finite, well-defined sum in our minds, isn't it? It's just the sum of the first n terms or whatever. So what we're looking at here is a sequence of partial sums. Is that okay? And the question is, does this sequence seem to have something that it approaches? I think the answer is yes. It approaches 0.333333. Oh, which is also known as 1/3. Is that what they say? So yeah, I think this we could say approaches 0.3 repeating, which is 1/3. But we really need to stop and smell the roses on this, okay? Because there's no. I think a lot of you, when you see this statement up here, over on the whiteboard, that we said from the warm-up, that this infinite sum equals 8, you're a little uncomfortable with that. You're comfortable with the language, this approaches 8. This converges to 8. This gets closer to 8. But when I say that this is 8, you're like, reject that notion, right? You're like, please, right? And yet, you have no problem saying that 0.3 repeating equals 1/3, right? You wouldn't be like, well, you wouldn't hedge, you wouldn't give like a footnote. You'd be like, yeah, 0.3 repeating is, like with a capital I, capital S, 1/3. Wouldn't you say that? With no footnote at all, right? And yet it's the same thing. In fact, what kind of series is this? It's geometric. The first term is 3/10, and the common ratio is 1/10. So use the formula. Do you get 1/3? 3/10 divided by 1 minus 1/10. Work it out. Do you get 1/3? 3/10 over 1 minus 1/10. Just work it out in your head. That'd be 3/10 over 9/10. Is that 1/3? But I think it works, is the point. I'm just saying, this is no different, in fact. It's like got exactly zero differences between this and the problem I presented earlier, and yet somehow you're uncomfortable with that. I say that if you're going to be uncomfortable with this, then you need to be uncomfortable with the 0.3 repeating equals 1/3 too. Okay, that's how it is. And maybe you are uncomfortable with that. In fact, it should be no business of the elementary school teacher to like say anything about 0.3 repeating. You should have like questioned the man back then, actually. Shouldn't you have? Yeah. Excuse me. You like in your little tiny voice, you would have said, "Is that an infinite sum?" And the teacher would have been like, "Do your work" or something. I don't know what they would have said.
Do 1 plus 2.
But you should definitely like rightly question the man, right? 0.3 repeating, that's like a deep, deep subject to add up an infinite number of things. We shouldn't have handed that to an elementary school kid, you know? So anyway, just wanted to speak my piece there. Let's keep going. What's the partial sums here? The first S1 is 5. S2, the sum of the first two terms. Everybody. S3. Well done, kids. Etc. Okay. And what do you think about the convergence here?
No.
Yeah, these numbers in this list seem not to be getting close to a number. So I think we're going to say this diverges. I also did tell you that this kind of series would diverge. It's a what kind of series? Yeah, and that'll happen with any arithmetic series. Down here, what are the partial sums? S1 is, what's S1? 3.
0.
S2 is 0. S3 is
0. 3.
very good, everybody. Okay. Yeah, and then, so the question is here, does this converge? And the answer is no. Do these get closer to a single number? And the answer is no. And keep in mind, remember that by limit we mean, does it get closer to a certain number? I mean, if you claim the limit is 0, say, then it's not. But if you claim it's 0, then there should be I should be able to say, okay, find a number after which, a place in the sequence, in this sequence right here, after which your sequence always stays within 0.005 of 0. And is there ever going to be a time after which it stays within that tolerance? Okay, then it fails, right? So that should be your, that's actually the definition of a limit, is that for no matter what the tolerance you give me, I can always find a place after which the function or this sequence in our current context stays within that tolerance. All right, this is a fun activity. What? Sorry, Daniel. Yeah. All right, fun activity. It's more of a thought experiment. No notes are required here. Yeah.
So if point can be repeating is 1/3.
Yeah.
So point 3 repeating times 3 would be 1.
Correct. Point.
But my calculator gave me 9. My calculator gave me 0.9 repeating.
Well, that's because the 0.9 repeating is 1, right?
Oh. Okay, I got you.
Yeah.
I'm trying to stump my fingers.
Is 0.9 repeating 1 a thing you've not thought about before?
Is it not arguable?
You can test it with the formula we just used. 0.9 repeating, it's 0.9 is the first term divided by 1 minus 1/10. You'll get 1, right? So that's one way to show it. Okay. All right, are you ready for my fun thought experiment? You are the paper master, okay? And you have 2 friends. They love paper. So you're a friendly paper master. So you give them each a third. Okay? Just listen and learn.
Wait, don't we only have 2 friends?
Yeah, you're going to give them a third, and you're going to keep a third. They loved your gift. And what they'd like is more paper. So, with the remaining piece that you own still, you're going to give them, because you can only be so generous, you're going to give them a third each of that piece.
They keep taking from me.
Right? Can you imagine? So the stack on the left is my piece still, and the 2 stacks, these are their growing stacks. And they love that gift, they want more even than that. So I'm giving them a third again, which by the way is what fraction of the original paper, the one I just gave them here. 1/27 now is what I just gave them each again. Okay? They do love paper, and they would like even more. So you give them a third again.
181.
And again, did I tell you that they love paper? And again, they love paper. All right, look at the picture, guys. Look at the picture. In the end, if you were to do this until the bright lights of infinity come, this stack, my stack, is going to be in the limit of size what? 0. And they will each have stacks of size. Yeah, all the paper is in their possession now, and there was 1 piece before, so each one has a half. That's the answer to this question and this question. Okay, but how much did you give them? Initially, you gave them a third of the sheet, and then a ninth, and then a 1/81st.
And then 1 2/43.
And then 1 2/43, etc. So I think you've just claimed that 1/2 is the same thing as 1/3 plus 1/9 plus 1/81st plus etc. Is that what you just claimed?
Yes.
Now prove it with your formula too, because that's a geometric series. 1/3 divided by 1 over 1 minus 1/3 is that 1/2. Check it out. Make sure it works.
Yeah.
Does it work? You ought to
Think
be.
it works.
I mean, it's funny because we never used the formula here. It just kind of came about naturally. You are the paper master.
Oh yeah, I got 25.
Well, there you go. Okay. I don't think you need a calculator for that operation, but we'll go with this. All right, please go. Add these up. I'll give you I don't know, 2 minutes to work on these, and then and then I'll call on some people here to give answers. I'll just tell you right now, all of these are geometric. Can I say that? So be ready. Especially if you're going to use graphs. I'm not sure you need your calculator for any of these. Maybe you want to avoid it.
Think about it, because 2 minus 2.
That's also known as 3 times, right?
That becomes 2 times
Yeah, but
1
that's-
half to the 1 minus 1.
Are we allowed to live in a fraction order? Oh, okay, well then, yeah.
Maybe you don't put a negative. That doesn't. Yeah, the first term is yeah. That might be wrong. The first term is 2. It honestly doesn't sound right. Seems wrong. I like the fact you checked the reasonableness of your answer. That's good. I like that. All right, so
2, right?
And what's the rate of change?
Chase, I've heard you like paper.
I do. I like paper. Oh, nice. Thank you so much.
Yeah.
And what is 2 divided by 1 minus 1?
I don't know. Look at this gift I got. Guys, it's on graph paper, so we could really accurately produce the sum of one.
Infinite number of options. Each one ordered by C. The first person ordered 1 C.
I like that one. Can we get Grace when you're ready? Can you give the first one? Anna, you're gonna get the second one here. Grace W, you get this one. You can just tell me out loud. And I don't know who that is, but they have a last name that begins with an S. Okay.
Oh, Luke Shia.
You don't have to give me any necessarily reasoning. What's the answer when you're ready? You want me to come back to you? Grace? Okay. Anna, did you get the second one? You want me to come back to you? All right. Grace W, you want to? You have yours yet? You're still working on it? Okay. Luke, you have yours yet?
No, he's wrong.
That's not the confidence we're looking for, young man. You gotta own it. All right, any of you 4 have an answer? You want to shout out, Anna? Does it diverge? I think so too.
It's always short and very.
Anyone else have an answer from my people? To what? All right. Check your answers up here. C. G-Dub. Do you have it? You gonna write it? Awesome. Go for it. And Luke.
Since it all adds up,
Oh, look at that. Using cheater. Oh, you're right. Okay, good job. Good use of, that's actually good mathematical instinct right there. Laziness, it's called.
Oh.
Strategy number 5, laziness. Use previous results. Yeah. Or you could do the sum formula. Then hopefully it will come out to 1.5. Or rehab. Does that work? Not bad.
There's a more precise answer. More precise answer.
Yeah, what is
It
it?
is a rational number. It's 4013.
4013.
Yeah.
For the last one, would that be different if the pattern started